Welcome back to video tutorial on AIOS. In this video, we'll be talking a very important topic for the current generation of AI models, which is nothing but model splitting across the nodes in a grid. So, grid or a cluster using the native libraries. Right now, for the current demo, we'll be using PyTorch and Transformers. We'll be using Jupyter Notebook for the entire demonstration. And in this notebook, you will get an overview of how to split the models in AI voice using library support from PyTorch and Transformers. This demo is for the users who have a larger model and they want to split those models if it doesn't fit in a single node or a single GPU. How to split it across the nodes? It's for them. And we'll be using a split SDK, which is an integration touch point with respect to AIOS and model splits. We'll be using that split SDK. I'll explain what all how the code of a split SDK looks like. So first of all, we need to understand what all different strategies are available, what all different parallelism is possible in current date. So I'll not go through all the parallelism supports available, but I'll highlight few parallelism supports. So first one is a tensor parallelism. In the tensor parallelism, as you know that the deep learning models or LLM models, they are basically a CNN layers, which consists of basically a matrix multiplication addition kind of thing. So if we can break down a bigger matrix multiplication into a smaller matrix multiplication, that is the fundamental thing for the tensor parallelism. So here you will have we'll be splitting a single operation. It can be a maximal, it could be any other operations which can be splittable. So maximal operations across multiple devices. A large matrix multiplication of is split across GPUs like feed forward network or attention blocks. So example, so let's say we have a matrix W which can be split into column matrix W1, W2, W3, W4, and this can be transferred to 4 different GPUs, and each GPU multiple inputs. Let's say, for each GPU weight, we'll be multiplying them with the input X, which will result in Yi. For X is input X is multiplied with Wi, which is number W1, W2, W3, W4, you will get Yi, Y1, Y2, Y3, Y4. And later on, we can collect all this all the Yi's, and with an high-speed communication collective, which is like all gather kind of operation, which will collect data from the output of the all the chunked weights. So once this is collected, then we'll get a final output. So this is the main the fundamental behind tensor parallelism. So all GPUs are active on the same layer W at the same amount of time. So if weight is split into 4 parts, or when the 4 splits are put it in 4 GPUs, all the 4 GPUs will be actively doing their computation. So what are the pros of this? So high GPU utilization keeps all the participating GPUs busy, because a big weight is split into 4 parts and they are divided across the GPU. So GPU has some task to do at any given point of time, and this avoids the idle bubble in pipeline parallelism. So no GPUs are left free at any given point of time. So that's what it is. So low latency, excellent for inference, as it speeds up the forward pass of an individual large layer. But not just that, there is a cons as well. So high communication overhead. Why? Because for, let's say, the every Yi, it has to come and gather together to give one output of that particular layer. Like you have several such layers. So because of this, lot of data get transferred from each GPU back to the the first GPU whomsoever gathers the result. So that's why high communication overhead will be there, which requires a frequent high bandwidth communication between GPUs. It is almost exclusively used with a single node connected by a ultra fast interconnect. Not just a single node, we can use the multi node as well. So, but yeah, it's better to provide NVLink kind of a hardware support for a faster data transfer across the nodes. And the second one is a pipeline parallelism, where instead of breaking the big operation, what they do here is breaking off certain layers. Like you have, let's say we have 20 layers. So let's say we'll divide it as 5 layers. So those 5 layers will be put in one GPU, other 5 layers will be put in another GPU. So this way they will split the whole layers into multiple GPUs. So the split entire model into a sequential chunks of layers and place the each chunk in a different GPU. So similar to assembly line. So you can take the assembly line into perspective. So where each GPU processes different micro batch of data when input is available. Output of one stage, that is X number of layers, will go. The output of that will go to the second one. So second, let's say the second GPU will now start processing the output of the last stage. So when one GPU finishes processing its micro batch, it sends the output to the next GPU, starts processing the next micro batch. So this way, the pipeline parallelism is achieved. But what are the pros? Lower communication volume, because only the last layer output, or the splits last layer output only will go from one GPU to other GPU, and scales across nodes very well, so can work effectively across multiple servers connected by a slower networking like Ethernet, making it ideal for scaling to a huge number of GPUs. But cons is a pipeline bubble that we have talked here. So when one GPU is done with its task, right? So it has to, when it gives the output back to the second GPU, the first GPU is left free. So if there is a mechanism to use that as well, then we can say a pipeline bubble will not be there in the pipeline parallelism. And load balancing is hard. The layer must be carefully divided. Uh, let's say you have an 20 layers, so we can divide it in properly with like five layers each. But what if you have a number of GPUs odd number, like we will not be able to divide properly. So that planning is required, careful division is required. So those are the the cons of a pipeline parallelism. And one other parallelism is fully sharded data parallelism, which is generally used for the training purpose, which I'll not talk here. And here in this fully sharded data parallelism, people use weight, not just weight, they will shard the gradients as well, optimize the state as well across the GPUs. And sometimes they call, there is on data parallelism also, which will be basically like replicating the model of splitted model, that they call generally in data parallelism as well. So that I have not added here. So next, the concept of rank, local rank, word size. So these are the words that we'll be using here and there. So we just have to understand what these words mean. So think your multi-node setup as a team of workers assigned for a larger project. So let's say you have some X number of GPUs and N number of machines. So those are the workers now. GPUs are the workers. So you can think this as those as the workers. And each worker GPU has a specific role. So each GPU has a specific role when either layers are divided or layers are cut into four. One matrix multiplication is cut into four half, right? So every uh, uh, task will go to a GPU. So we call them as a worker, and works on a portion. Each GPU will work on a portion of a data. It could be a complete layer, or it could be a split of a big matrix multiplication. So here world size is this is the total number of workers. So basically how many number of GPUs you have, that many number of workers you can create. So that's what we call it as world size. For example, if you have a 2 node with 8 GPU each, world size is 2 times 8, which is 16. And rank. So to give a numerical number to the each and every workers, right? So we use the rank here. So this is the unique identifier for each worker in the team. So since there are 16 people, it will start from 0 to 15. So this is just for a distinguishing sake. Say the rank 0 is the main guy who will take the input, and rank 15 is the guy who will give the output, deliver the output. So local rank. So within the node, let's say since it is spread into machines, so within the node, what is the ID for each GPUs? So that's what is about a local rank. If each node has 8 GPUs, then the local rank for the GPU in a single node would be 0 to 7. So there will be local rank 0 to 7 in GPU node 1, and same as 0 to 7 in GPU node 2. So to utilize this Jupyter notebook, I have created some variables here. So let me just run this variable. So they will initialize the variables that we'll be using later on. And to model splitting in a multiple GPUs on a same node. This we have already, we have several videos how to split a model in a same node on multiple GPUs. So this will, with the help of libraries only, we'll be able to do it. Like say you have a PyTorch, Transformer, or Llama CPP sort of libraries, they will give that capabilities to you. In a node, you have multiple GPUs. To the model, you have to just mention the IDs of the GPU. So that way you can load the model on the same node. So if you still need a example for it, so I'll just, we have given a example here for Gemma model onboarding. So you can just check our allocation.json file. So where it uses, it gives the two IDs 0 and 1 from this node. So this allocation JSON is used for allocating the model in AIOS. So here we'll be providing those GPU IDs to the model in this particular node, and this data will be used by K8s to pass on the GPU to the block that is going to do going to load a model. So since libraries has the support to take multiple GPUs, right? So they will take those IDs and they will load they will split the model in those GPUs. So that I'll not talk here because already several videos are there. I have given a link as well how to do that. So we need to mention GPU IDs in allocation JSON, and the rest will be taken care by the library itself. But right now our focus is on splitting across multiple nodes. So let's begin the understanding code sample of splitting and generating the response. So I have given the link for the code here. So we have something known as a split SDK. So what the split SDK contains? So if you see the main, there is nothing in the main basically. So here we are calling AIOS Transformer APIs dot import main, and main is called. So if you see here, the main codes of transformer split SDK is API.py, which is there in the AIOS transformers, which will expose a REST API for a model inferencing, because AIOS has to be an inference server as well. And also this SDK.py will take care of splitting the models and running the models, and this will be acting as an inference engine, then this will be acting as an inference server. So AIOS Transformer SDK contains core logic for model splitting and distribute the inference. And here there is one file, metrics.py file, which is for a metrics calculation, metrics utility. So let me go ahead and show you the main.py, sorry, the apis.py. It is available in the AIOS Transformer. So in the main.py, we have a function main, and it has a distribute inference SDK. The object is created, and this file is coming from the .sdk.py. So we'll get into this details of what this contains, but yeah, basically we got an object of the distribute inference SDK class, where we are passing a model name and a task, whether it's a generation, embedding generation, or what. And so if rank is 0, so this is what very important. If the SDK.rank is 0, the current when a model is splitted into multiple ranks, the 0th rank will have a lot of works to do. So that guy has to expose an inference server. So right now we are using an Flask app here, and it will create an app with an endpoint generate and set config. This for mainly for updating any configurations, and this is for doing the inference. So these endpoints are responsible for interacting with the user or any other blocks of a AIOS. So this basically, if you see here, it has a SDK.distribute generate function. That is the main, the core of core logic falls in. So that is a responsible. You will send the prompt to it, the input data and generation config, and you will get the output, and that will be passed here. That's it. So set config is just to uh, set certain configurations you want. So these are the base two endpoints we have in this file. So let me close it. So let me go to the SDK.py, which is a core logic. So here we have a class distributed inference.sdk, sorry, inference SDK. So it takes a model name and task and metrics. If it is none, we'll initiate it. So first we are taking the rank of it. This rank variables, this rank and local rank are passed by AIOS to this container. So you don't have to worry. So that will be collected, and we'll be using those variables. And torch CUDA sets device local rank. So we are setting whatever the local rank local rank is basically a GPU ID in the that node. So that will be set here, and a device is created, which is a torch device. CUDA device is created because the model requires a CUDA, and which is nothing but NVIDIA GPUs are required. So we are creating a CUDA device here. So right now we are importing one very important library here, torch distributed dist. So as a dist, and this is what we will be using for mainly communication between the ranks. So whenever rank is about to do any inference, right, it requires certain informations. So how to split the model, what is the input, what is the how to give the output of each split, all those requires some backend library support. So that's why we are using a torch distributed, and we are using a transformer library to for the tokenizer and loading the model of the transformer model. So here these two lines are very important lines, where if a distributed library is not initialized, we are initializing a process group with an NCL as a backend. So NCL library is being used for a communication within from within the chunks, within the splits. So a tokenizer is created using the auto tokenizer from the if you give the model name, it will open up the tokenizer, and certain initializations for the tokenizer. Then if generation is a task, then I'll create the model, auto model for causal from pretrained. I'll give the model name. Right now I'm giving torch floating point 16 b float 16 as a the model's precision, and auto tensor planning is auto. TP plan here is auto, so that torch will take care of so the transformer will take care of distributing the layers. So if you have good hands on with the libraries or the transformers, so you can try to give a your optimized plan, auto plan, so that can be passed as a maybe a parameter for this particular function. So a model is created with the help of transformer library, and by default initializing some generation configs. So this will be used by the model while doing the inference. So I have a very important function here, distributed generate. So what it takes is prompts and some RQW arguments. So prompt is what the user types query, and if that is none, we'll be keeping as an empty. So if rank is 0, as I told, the rank 0 has a very important task. So if rank is 0, it does some operation. If rank is not 0, because this container, this code will run for all the 4 ranks, and based on the rank they will do their task. So if rank is 0, it's going to do something. For rank is 0, I'll take a copy of the default generation config, and whatever the keyword arguments I get for a current generation, so that I will update to the default values. Then I'll create a JSON string out of those dictionary. It is a Python dictionary. I'll create a JSON string, and then I'll convert those JSON string into bytes using string.encode, where UTF-8 is the encoding standard, and those bytes are converted back to the tensor, PyTorch tensor. Uh, Before that, they are converted into a list of integers. Basically, right now, this bytes will be in terms of they are basically byte is basically 0 to 255, right? So those numbers are like whole byte JSON byte data will be converted into an integer array, and then we are since it is an array, we are creating a tensor out of it, and since it's a byte data, UTF-8 is a byte data, so it's a byte tensor. So we are converting the byte tensor, and we are transferring that to the device as well. So this config.tensor has a content of the generation config in terms of bytes, and to calculate how many elements are there in that tensor, we are using the numeral operation. So config tensor.numeral, which is the number of elements, which will get the total length of the this particular byte tensor, and that also we are creating as an one variable, and we are passing that to device. Here is a CUDA device. This is an long integer, 64-bit integer. So this is for the rank 0, and for not 0 ranks, so any other ranks, we are simply creating this variable only, config size, which is of 1 value, and it's the torch long, and it's in device. We are just initiating a variable known as config.size, which is of torch long type. So because since I don't have to, it is just the number, it is not like array or anything. I don't have to allocate multiple content. I just require one long is enough. So now this dist barrier, so this is basically from the PyTorch distributed dist barrier. What it does is it will try to synchronize all the ranks to stay here until unless let's say out of 4 ranks, 1 rank is in crossing here, and uh, let's say well, 0th rank is doing all this operation and all other ranks are doing this operation. They will come, they will finish first, and rank 0 is still doing some operations. So basically this barrier will synchronize, it will make other ranks to wait at this point of time. Once all the ranks are available here, again it will continue. So right now after the dist barrier, we are calling one function save all ranks, and what I am passing is one dist dot broadcast, which is a callable function, and a config size and a source 0. This is the keyword argument, and it is a argument. So let us see this function. This function is written here. So save all ranks, it takes an callable function, and it will take the some set of arguments, and it will take some set of keyword arguments. Keyword arguments is you have a key and value pair. So first what I try to do is I'll try to allocate one dummy tensor, torch tensor, and that on a CUDA device. So if that is success, great, meaning I'm having a control of the GPU. I can allocate a variable, and this variable is used to do some operations that I'll explain later. And then a callable function is called with the arguments and keyword arguments. So it could be any callable function from the maybe dot distribute or any their functions, a callable function, and its result is collected. If this throws any exception, then I'm making success of 0 equal to 0 and result to none. And I'm so now once I make this, I'll do an synchronization again. So distribute all reduce. So basically it is synchronization global success status across all the ranks. So what I'm doing here is success variable I'm passing to this particular function. So this success variable comes from the all the ranks. So let's say 4 ranks are there, all the 4 ranks provides one variable success, and in that I'm trying to get the minimum value. Why minimum value? Because if any failure happens, right, I'm going to make that value as a 0. If no failure happens, everything will be 1. So since I'm taking the minimum of it, the minimum will come back to basically failure case, and because of that I will get to know whether since I'm going to reduce the all the success from all the 4 ranks to minimum of it. So and then I'll compare that minimum to a 0. If it is 0, then definitely one rank or maybe multiple ranks would have failed, would have raised a exception. That's why I'm getting a 0. So that's why I'm again doing a dist barrier. I'm waiting for all the ranks to available here and destroy the process group. And if success items not having a 0, it means all success were providing ones, then this operation is success. So that's why I'm returning the result here. So this is the function. Basically you wait for the try to allocate one variable, success variable, across all the 4 splits, and call that function. If it is a success, great. If it is not, an exception is there, we initialize that success variable to 0, and then reduce all the 4 successes from the 4 splits to get the minimum out of it. If when you get the minimum out of it, if it is not if it is 0, it means it's a failure. If it is 1, it means it is a success. So return the result. That's what this function is all about. So now I'm going to call that function. I have done a dist barrier, and I'm going to call that function, and I'm doing a broadcast. Broadcast is sending across all the chunks, all the splits. What I'm sending here is a config size, and the sender is a source 0. So config size is just then torch long, so it is one single integer of 64 bit that I am broadcasting, and it will be, once it is broadcasted, great. If not, exception will be raised. Say broadcasting is proper now. Now what I'm doing is, if rank is not equal to 0, other ranks 0, I mean 1, 2, 3, 4, all other ranks, they are going to create an torch.empty with an config size item. So because the config size is now passed on to all the splits, now the content of the config size is available. Let's say now this config size was 100 bytes. Those 100 bytes is available across all the 4 splits. Now that with that value, I'm going to create an config tensor. I have not transferred the config tensor at. I have just transferred the config size to the all the ranks. So now I'm for all other ranks, I'm going to create a config tensor variable. Right now I'm initializing with empty, basically nothing, and it's on self device. This guy is again integer uint8 because it's a byte. We have encoded the data right into byte tensor, so I'm creating a uint8 torch d type here. And now again I'm doing a barrier operation. Basically all ranks will wait here, and I'm again calling a save all rank again with the same similar function, disk dot broadcast. And here right now I'm passing the config tensor, the tensor which we created, byte tensor, right? So that I'm passing it again from source 0, the source 0. So now once this function is called, all the ranks will have the config tensor with them, and with that I'm going to create again, whatever the operation we did, right? I'm just reversing it. So from the list I'm trying to get the bytes, and from them I'll try to decode it to a uint8, and then I'll do a JSON load. So now again I have a config dictionary with me. So this dictionary is available now with all the ranks. So this is the operation till now we have done. So basically you pass what is the size of this generation config, and then pass the content of the generation config. So now let us do a tokenization. The tokenization is basically converting your prompt to a tokens. So now the only one guy will do that, which is the thing with rank 0. So other guys will not do anything with the tokenization. So they will not do tokenization. So that's why for rank 0, I'm initializing the tokenizer. I'm giving the tokenizer with the prompt tokenizer initialization happened above. So I'm giving the prompt return tensor pt padding false. So I got the encoded tokenized content, and from that I'm trying to take the input IDs and attention masks, and also I'm trying to take the length of the tokens. So let's say if the prompt that you are given is converted to 100 tokens, so now I'm trying to take that length, and this length I need to pass on to all the ranks so that they will initialize the memory accordingly. So right now I'm going to create the length of the input shape, and it's again a long one single integer with of 64-bit again in the GPU node only, GPU memory. So prompt length is created in the rank 0. Other ranks I'm just creating an empty variable of a torch long. So right now the content is not available. Similar approaches I'll follow. Dist barrier and save all ranks. Dist broadcast is called. Prompt length is passed this time, and from the source 0. So once this is called, all the ranks will have now the prompt length variable, and if not, self rank is not equal to 0, I am creating the empty dictionaries of input IDs and attention mask with the prompt length as a number of the number for the empty array. So I got an input ID mask, empty attention mask, which is a empty now, not having any content. So I need to get those content, right? So again, rank 0 has to send the data. So distribute barrier is called, save all rank is called, distribute broadcast is called, input IDs is passed, and attention mask is passed. So at the end of this line, all the ranks will have input IDs and attention mask is there. So now let us do the inference. So because all rank has the input IDs, all rank has the configurations, all rank has the attention mask as well. So with that we will create an inference. So before creating the inference, we are trying to do unquiz, meaning like we are trying to add one more dimension to the current inputs. Because it was an array, we are creating now different one more dimension to it in the same device, whichever the ranks are having each GPUs, right? In that GPUs only we are creating a increased dimension, one more dimension. So with that I'm calling again the save all ranks, and now the callable function is self model generate. So it's the generate function of the transformer library. So that is being called here as a callable function, and I'm passing two keyword arguments, input IDs and attention mask. The input will be passed to this particular callable function, and also the config. The config here is nothing but the generation config for the inferencing. It could be like these are the configs: max new token, do sample, top k, top p, temperature. All those values will be passed over here. So now this function, as you know that it calls this function with the input IDs given to it, and with the configuration it takes. And once that is called, all result of all the chunks will be collected in this function, and if success operation is true, then we will get the result. If not, we will get an exception will be raised. So that is the output here, that once success is true, so we'll get output, and we are calculating a duration for a matrix. So if output is none, return none, and if self rank is 0, I'm just creating a matrix. So we could have created this matrix here as well. I just missed it. So if rank is 0, I'm updating the matrix using record matrix function, which is here, which uses the matrix class available in the that matrix.py. So we are creating the the matrix, and that's it. So return output text or return none. So only for rank 0, I'm returning the output text. Other ranks will return none. So this is how 4 ranks, I mean n number of ranks will synchronize themselves to create an inference result out of it. So this is the SDK py dot from here, SDK.py. Right now we have not done any optimizations, like say a torch compile kind of optimization. We have not done. So for to know more about optimizations, I'll share you the link. Maybe you can go ahead and add those optimizations here. This is a vanilla plain simple code, just for a demo sake. So now this is the split SDK we have, and right now that split SDK I need to build it. So how to build that split SDK? So I just have to call this function. I have already built it, so I will not again call this cell. And once cell Docker is built, right, without any issues, so you just have to push it to the registry so that we can nodes can pull it. Any nodes can pull it, because this Docker image has to be available across all the nodes that you are trying to split, right? So that's why you need to have this image in the registry, or else at least you copy those images in each node. So right now, yeah, the Docker is created, Docker is pushed to the registry. So now deploy the model splitter for inferencing. So to know more about APIs, right, so I have provided a link here. So this is our the GitHub, where it's model split score API.py. You have certain APIs here: split create with policy, split create with policy dry run. So those APIs are there, like similar to split delete and the deployment name, split query, so you can query the splits. So several APIs are there. I suggest you to go through it, but what I have provided here is one split create function. And this in the split create function, it takes several parameters needed for to create split. So one is a rank 0 cluster. Let's say we provide, why this is given is, let's say in the future we across the cluster we want to do, right? So who is the rank 0 cluster ID that is needed, so that variable parameters available, in which cluster ID you want to deploy this splits. So there is a cluster ID, deployment name, you can give any name of your choice, number of nodes, basically 4. I'm going to create a 4 splits out of it. HF token, if model requires as HF token, you can provide the HF tokens. Common param, so model name, what is the model name? Let's say Google Gemma 227-bit 27B instruction model. Image, so this the image that we have created, right? This image is going to split the models across, and they will take care of synchronization using PyTorch and Transformer library. So master port is 3000, and how the splits are. So here it is. So per rank params. So this is rank 0, rank 1, rank 2, rank 3 are given here, and so for rank 0 it should be in one node, GP node 2, and rank 1 is also in GP node 2, whereas rank 2, rank 3 are in GP node 7. Basically I have two nodes with 2 GPUs each, with their 880 800 GPUs with 80 GB. So in that I am trying to split this model in the two nodes with 2 GPUs, and NCCL socket IF name. So basically it's an Ethernet. Ethernet will be used for the NCL communication. NCL will use the Ethernet to transfer the data from one split to other split. So NVIDIA visible devices 0 and 1, and CUDA visible devices 1. So the first CUDA visible device, I mean first GPU ID is used here. The rank 1 uses the GPU ID with 1 as a tag, and a cluster ID is given here. So yeah, so rank 0 0 GPU, and CUDA visible device also 0, whereas rank 1 NVIDIA visible device is 0 and 1, but within the process it will use the one GPU ID. This will be used by the AIOS to transfer the GPUs, the process to take the process which is running in the split SDK, right? So they will be given it both the GPUs, but in that we are asking it to take the first GPU as a device. So similar to rank 2, we have a GPU node 7 Ethernet interface for NCL backend communication, 0th device in the disk cluster, and CUDA visible device is 0. Whereas in rank 3, so 0 and 1 both the GPUs are given to the third rank, but in that we are asking it to take the first GPU. So this is the parameters right now I'm giving manually. I know that those machines are free, there is no content is going on, so that's why I'm creating this manually. And multi-cluster right now it's false, and platform is torch. Let's say in the future any other platform comes like TensorFlow or something else, we'll be providing those details here, like TensorFlow or something like that. And since right now, as I told, I am creating this manually, but to automate this in AIOS, right? So we have certain other APIs as well. So as I mentioned, uh, let's say split create with policy dry run. So this APIs can be used to estimate these values, like how in which GPU something is free, I mean which node GPUs are available, in which node which GPU I need to choose, whether something is going on, RAM is available or not. For all those calculations, we have a separate API, split create API. So this API will get data needed by basically you need to create a policy and you need to run this policy. You need to supply those policy details here to this endpoint. That policy will run and pull all the metrics required. The AIOS will supply all those metrics. It is similar to one other video we have that you can like to know write the policy for allocation node and GPU requirement, right? You can check this link. So this will give you a basic idea about how to write the cluster allocation, sorry, the node allocation policy in the node, what GPU to choose. This we have already explained in one of our video, so you can check the video. Also, video link is also shared. Around 43 minutes, you can directly hop on and check how this code works, what all we are doing in that code. Basically, it was for a as a reassignment policy, but similar policy can be used for a resource allocation as well. So basically that kind of policy will be writing to automate this flow. Right now, since I had known only two hardwares that were there with me, so I am doing this manually. So this is for one model. If in case you want to try some quicker, right, so you can use this feed 128K2 model as well. So this is the whole API. These are the parameters of the API. So let me run this model right now. So yeah, the deployment fee 128K2 is deployed. Let me check the pods created. Let me see how many pods are getting created and what GPU nodes they take, whether they are proper or not. Let me go to one node where I can run this command. It is in GPU node 3. Let me run this command. Yes, the 4 pods are created as images were already pulled. It was not in waiting state, it is already in running state. Only one pods are there, rank 0, rank 1, rank 2, rank 3. That's how the pods are given a rank. And if I just give O wide, so you would see what they are in which machine they are running in. So the GPU node 2, GPU node 2, first 2 ranks, and next 2 ranks are running in GPU node 7. So let me just show you the NVIDIA SMI as well. So this is GPU node 2. In that 2 GPUs are taken and around 25-26 GBs are taken, and this is GPU node 7. Again same, around 26 GB is taken. Sorry, not 26 GB, it is a 2600 MB is taken. So let us do the inference right now. So before going to inference, so we can directly do an inference to this endpoint, because the endpoint is already available with us, which is like which I have shown you earlier, the APIs. Generate API is available. We can always hit this pod, the rank 0th pod, and we can get the output. But to do that, I mean, we are having one more concept known as proxy AIOS blocks. So I'm using a proxy AIOS block, which is basically can do inference with a splitted model rank 0. Since I'm creating an AIOS pod, this pod will be able to communicate to the rank 0 pod in internal network. And also, if you want some sort of a history kind of a chat kind of a interfaces, right? So the current split version will not provide that. So to minimize the coding things, we have not put all the history related things there. So for that reason, I have a proxy block to maintain the history for a chat interface kind of a thing. So proxy block can be used for that history and kind of logic maintenance. And also proxy uses internal namespace based on URL for inferences. So and if not, we need to create a cluster IP to node port for a model split port services. Basically right now that port is not having a node port, it is a cluster IP only. So only with the internal components of AIOS only can talk to the endpoint. So right now the service whatever is exposed, right, it will provide a cluster IP only. So to either I need to change that cluster IP to node port to talk to that particular service, or I can create a proxy block. Proxy block can use the the namespace based URL for a inferencing. So that's why I'm using a proxy block here. So the endpoint URL generally look like this. The deployment name of the splitting service, that is what we have given here. Let's say if 128k2 is a deployment name, that name will come here, and the rank master svc dot cluster dot local 8080 generate. So this is the endpoint that this model the proxy block will hit to, and that will reach the rank 0th pod, which is having a service in it. So let me show you the code of the proxy block. So it is not a it's very simple code. If you have seen our other videos how the block code will look like, it is similar to that. So the block client code. So basically it has it will take the block init in parameter settings, and those are variable initialized here, and block system message if any system message is available by default, right? So you can keep those system message that we can supply it to the model. And you require a model split ID, which will get as a from the API, sorry, from the AIOS you will get that information to model split ID. And API. So this is the API, the model split ID, which is basically nothing but a deployment name, rank hyphen master hyphen splits svc cluster local 8080. This is the whole API this block will do the inference on. And on preprocess, this we have you can see some other videos of how they are on preprocesses function is creating a before the actual inference. On preprocess will do a lot of things, basically extracting certain informations needed, or creating a packet that is needed for inference. All those tasks are done by this on preprocess. It is basically pre-processing normalizing work. And if in case a mux operation is there, or a input is getting splitted from input is coming from two different blocks, so how to handle all those data. For that only we have a on preprocess function, and we have another function is on data. This is what the main inferencing function is. So I'll not explain much on process. I'll go directly to the on data. So in the on data, I'm trying to get session ID and input. So this session IDs are put by this here, like session ID packet dot session ID is put here. So I'm extracting session ID and input data from the preprocessed entry. So because the output of the preprocess will go to the on data, and that only I'm using it here. And I'm taking the message, which is basically input that is passed on in the input data of this preprocess entry. Sorry, the input data available in this preprocess entry, and the mode, basically chat mode or embedding generation mode, token generation mode, what mode. Right now, I guess we have only one or two modes, chat mode or a generate mode. So whether it's a mode or chat or not, based on that, we have to call a different endpoints, and we need to pass on a different inputs to the API. So here generation config is taken from that input data, and if not, by default values are given here. And then if message is no message is there, then we are returning the empty result. If mode is not available, we are returning false. Those kind of boundary condition checks. And if mode is chat, I'm trying to create a system message, which is I'm creating a uh, I'm trying to get a system message, and I'm creating a history variable for which I'm adding role and content. And um, this the when the session ID is not there, right? So session ID is one unique integer for the current session of chats. So if that is not there, we are going to create a session ID key in the chat sessions, and this is our chat history. First message is always a system message and the content of the system message. The system message is taken here from the either you can supply the system message from the input data, or else it will take the default system message. Then once the variable history is created, you will add the user role. So right now it was a system role, and right now it is a user role which user is prompting. So that message is put here, and payload is constructed. Payload has messages enable streaming generation config, and generation config is passed here, and this the URL. So this URL is of a v1 chat kind of a URL is available here. And next, right now, I mean, we have not supplied this v1 chat kind of a URL in our API. So I'll not be using chat interface. I'll be showcasing only you the generate interface. So if it mode is not chat, we'll go to the else part. So in the else part, basically this endpoints and all we can put in our APIs. So how do you want? You can paste that. Right now I'll be showcasing only the generate endpoint. So a prompt message is taken, prompt, temperature, max new token, do sample, top k, top p, everything is put in payload, and that payload is passed on to the generate endpoint. So here, once the response is received, the URL is this API is already constructed above, and this slash generate is what we are going to call, and the response is passed and sent back. So if since it is an else, we'll get result of output, and that is passed like a output generated. So this is the simple the simple block. It is simply as a proxy block only. It is not doing any heavy lifting. Just take the input and pass on to the split model rank 0 and get the response and send it back to the user. So I have built that client Docker as well. The block proxy blocks image container image. I have built it. I have pushed it. And now to register. So I'll just show you the registration files which you are already familiar with if you have seen our other blocks. So this is the component JSON. So how this registration file looks like, I'll explain. So it has several keys: component ID. So PyTorch runner is a component ID, and release tags versions. So it has init data, which is like I have given the model name as split. So any init data you can pass on, and you need to tap on this init data in your code basically. So that init data is this is the init data, init params and init settings. So that will come from here. So the component JSON is during the registration time. It is a fallback mechanism, meaning like for actual allocation of the model, we have a block.json. But if block.json doesn't provide any content, right, then the fallback mechanism is component.json. So component.json items, I mean the content will be used in the code. The AIOS will take the fallback values if block.json doesn't have those contents. So this component JSON is used for registering the component. So you need to mention what all input it takes, how is the parameter structure, what is the input protocol, what is the output protocol. Protocol here stands for the syntax of it. So this let's say the component input protocol, it takes message, mode, system message, generate, config, 4 keys. Message is basically a string, mode is basically an string, system message is also a string, and generation config is an object. And it has again sub properties: max new token, top k. All these properties are available. Again, they are what are they? They are integers, floating point numbers, something like that will be mentioned. So this is the component input protocol. Similarly, we have a output protocol. What output will come, right? Its structure has to be given, reply or generated. Two keys can be there, which is like both are string. So for chat, maybe it is reply. For generated generation, it could be generated keys. And similarly, input settings protocol. So settings, there is only system message, and nothing else is there in the settings right now. And component management command templates, like if you have any functions, right now I don't want to explain that any function, so I have not given any important functions. And component parameters and component settings. So whatever the initialization, the structures you have mentioned here, so what all those contents. So component init parameters, I'm sending only generation config, and component settings parameter, I'm sending only system message. If for other values, if I'm not sending here, they will come from the component the component JSON will provide those values. So similarly, I have already registered this. So to register the component, I am using a component registry service API register component. So it will take the component JSON and it will register this particular block. And to unregister, you can run this command. So I've already registered. I will not register it again. And to deploy the block, so let me deploy this particular block. As I have already deployed the split SDK, I have not deployed the block yet. So let me deploy the block right now. So block is created. So this block will take the image that you have created here, which is nothing but PyTorch split client latest. That is the container image it will use. So let us see get the logs of the block. Let me just kubectl logs. Before that, I should get kubectl. So this is my sorry. Yeah, just let me see what is the name I have given. So that we have to check it in block.json. In the block.json, I would have given PyTorch block 3 as the name. So that's why we have got the PyTorch block 3 here, PyTorch block 3, PyTorch block 3, 29 seconds back, right? So they are running only. So this 6 by 6 and 2 by 2, actually this 2 by 2 is actual our instances. It will have containers like instance and Redis, which is basically an queue between the actual block and the instance. And here the 6 by 6, they are containers like, again, it will have its own Redis, executor, load balancer, things like that will be available. Stability checker, pods will be available. So that we have explained in the video meant for a tutorial 10, so that you can check it what all containers are available. So right now the pods are created, the block pod is created. So let me just check the log of this block, and in that block I'm going to check the instance pod. So let me just take that block. So this is the pod, I'm going to take it, and I'm going to check the logs. So I have to give the instance container. Yes, the model is available and ready, and health endpoints are coming and hitting. That's how the AIOS will try to check whether the the health of the block is available, I mean healthy or not. So it will try to hit the health endpoint. And so now let me do the inference. For doing the inference, again, uh, we cannot directly hit the block like that. So you can use the inference server, or else you can use the gRPC rest gRPC endpoint of the block. So right now I have already created the inference server. How to create the inference server, I have given details here. So you need to create the namespace for inference server, and then deploy the YAML file for the inference server. It is if you have a multiple inference server on a single, I mean you can have a single inference or multiple inference server per cluster based on the number of hits you are receiving on an inference server, right? You can scale it. So right now I already created the inference server. I'll not create the inference server again. So I'll do I'll hit the inference server with v1 slash infer as the endpoint. When I hit that, and then I give the model as a PyTorch block 3, that's what I have created here. And I have to pass some session IDs, and I need to pass some data. This data is nothing but the input data. Mode is completions, and generation config, I'm sending some generation config. So let me the message that I'm asking is a to give some Python code for a integer list adding, and system message, you are a helpful assistant, that provides a code examples. So this is my input to the inference server. This is my payload to the inference server. Inference server will pass on this inference request to the block, and then block will talk to the splitted model and get the result back. So let us do one inference now. So I have given the PyTorch block 3 session 3. Let me just increase it to session 4, and sequence number. This is always a monotonically increasing number. So you just have to make sure after one inference you need to make the number increasable. One other important parameter I forgot to inform you is this, the deployment name. This has to be given in block.json, or else the block.json the as a model split ID, or else the block will never know to whom to talk, I mean how to replace the block init data. This model split ID, how to replace it, it doesn't know. So you need to provide this. This is a deployment name that only will go to our main.py and will replace the actual URL. So that is important. And let me do the inference now. Okay, let me just bring the, so yeah, some utilization is going on in the GPUs. Some utilization is going on. Yeah, some things are going on. Number crunching is going on in the GPUs. Let's wait for some time. As I told earlier, like we are not done any optimizations. You can change a b float to maybe a into-bit integer inferencing, and also optimizations related to the data transfer, or anything related to the distributed inference. I have not done anything. It's a vanilla simple plain. So inference is done now. So you can, we have got the output as a generated key, and it gives some content. So this way we can do the inference. And right now the model is fitted in 4 different machines with tensor parallelism of 4, and you can change this to even 2 also to run it in same node as well. Maybe if in case you want to see it, let me just show it. So first I need to delete the cleanup APIs are here. So delete model split first, because I want to change that to two tensor TPs. So let me delete the model split. Yeah, it got deleted. So let us wait for so let us check the splits. Yes, yes, it is in the terminating phase. Let it get terminated. Yes, it got terminated. So let us run it again with by changing the input. Instead of 4 splits, let me change it to 2, and let me run it in single machine. So I just have to remove the last few chunks only. Let me just cut it. So I don't have to modify anything, because they are in proper numbers only. So let me just run it. So it has to supposed to run in only GP node 2. Let me pull the GP node 2. Yeah, this is the GP node 2. Yes, the model is loading. Let me show you GP node 7 as well. Yes, GP node 7, nothing is going on. So only GP node 2 model is loaded. So let us you can log this Docker containers as well. In the split namespace, these models are created, right? So you can always log those rank 0 or rank 1. You can check what's going on in those models. Let me do the inference now. So I have not deleted the blocks. Blocks are still available. Same blocks only I'll be using it. Only what I deleted is the split, not the block, the proxy block I have not deleted. So I can go ahead and do the inference as well now. So let me do the inference. So let me change the session ID to some 7, and that's enough. I get sequence number. I don't have to change it. Let me just run the inference. Yes, something is going on in both the GPUs parallelly together. So if you have loaded this model in the single container with let's say just the transformers or with the llama cpp, the result would have been faster. But right now it is not faster because we are using pytorch distributed as well, and also the optimizations has not been done. It's a vanilla simple code. So yeah, we got the response. So, yeah, the cleanup, I have shown you how to delete the model as well. You have a split delete, and you just have to give the deployment name. And to delete the block, it's like as usual, gateway URL controller remove block, and you need to give what cluster it is, cluster ID, and what block you want to delete. So that way you can clean up. So I have given the example for a Gemma 2 model as well. By you need to provide the token of yours because they are gated the models from the transformer. It requires a token. You can run this as well. I have given a more deployment name model split demo. So this you need to put it in block.json and you can run it. You can change it to even maybe a llama model or any other model also. You can change and check this. We have tested for multiple models. So just to show you the results of the Gemma model and llama model, I have here data. It is based on PyTorch and Transformers. Maximum token have tested 512. So with the rank 2, the rank 2 is in single node, two GPUs are used. For rank 2, the RAM GPU RAM usage is around 140 GB, whereas for rank 4 it was 148 GB. And I've tested it in 800 nodes, and number of nodes 1, number of nodes 2. So the query was consisting of, basically this was the query: give me a code adding two integers list element wise in Python, similar to Java and same as a C++, one after the other, just by changing the sequence number. So it was taking quite a bit of amount of second time in second here, 209 second, 195 seconds. So if I convert this to a tokens per second, right, roughly they are 2 or 3 tokens per second. So this was our llama model 70B variant, and this is a 27B variant, where the tokens per second was like a little bit higher than the Rama because of the smaller version of the model. So this was my result, and if you do all the improvements of the optimizations, we will definitely get higher. So just to summarize, what we have showcased to you in this video is demonstrated how to split a large model across multiple nodes using vanilla PyTorch and transformer libraries without any library level optimizations. Demonstrated how to create proxy AIOS block to do inference with splitted model rank 0. This will talk to the rank 0 because rank 0 is hosting the inference server. AIOS integration with model split API for PyTorch and transformers were shown. Inference server, so provided by AIOS, inference server is provided by AIOS, and inference engine provided by the transformer and PyTorch combo were also shown. And for further exploration inference optimizations, I suggest user to go through this link from the transformer, as well as to understand the distributed inference using transformer. So you can go ahead this click the link and read the article on